this video we're going to be looking at parametric curves, and first we're just going to quickly review the basics of parametrics. So parametric equations is when basically we take the x and y components of a function and we separate them into different functions of a third variable called the parameter. And often the parameter is represented by t. And so as the parameter increases, the curve will go in a certain direction. Then that direction is called the orientation. So let's look at, we have here two parametric equations. One describes the x-coordinate of the graph in terms of t, the parameter, and the other describes the y-coordinate. So there are two ways to graph parametric curves. You can either plug in values of t and then plot the x and y coordinates, or you can eliminate the parameter and get the function just in terms of y and x. So we're going to eliminate the parameter. So to do that, we have to write t in terms of x by just rearranging this first equation. And then once we have t in terms of x, we can just plug that into the second equation and then simplify. And then we just have a regular function with y and x. And then we just graph it like normally. And so here is the graph of these parametric equations. And you can see the orientation is represented by these arrows. And we can find out the orientation by seeing that as t increases, x increases, and y increases too, which means the orientation must be going this way as t increases. So we can represent any ordinary function in parametric form by just introducing a parameter t equals x. So you can see here we have a function, and then we can rewrite it as one of the parametric equations will be x equals t, and in the other one we just replace all the x's with the new parameter t. So that's just a basic overview of what parametrics equations are. If you don't really remember them, you should review your pre-calc notes. So to find the derivative of a parametric curve, all we do is take dy dt divided by dx over dt. And this makes sense intuitively because if we have dy dt and we divide it by dx dt, then the dt's will cancel out and we just have dy over dx. So let's look at an example. We want to find the slope of the tangent line to the unit circle when t is pi 6. So the unit circle can be represented with parametric equations by x equals cosine t and y equals sine t, because the unit circle is just a circle with a radius of 1. So if we do, and you can see how they're the same because cosine squared t plus sine squared t is just 1. So first we differentiate the x and y equations separately with respect to t, the parameter. And we get dx dt is negative sine t and dy dt is cosine t. So then by this equation, all we have to do to get the derivative of dy dx is divide dy dt by dx dt. And so we get cosine t over negative sine t, which is just negative cotangent of t. And to find the slope at when t is pi over 6, all we do is plug in pi over 6, and we find that the slope of the tangent line is negative square root 3. So just looking at this equation, we can also tell that if dy dt is 0 and dx dt is not 0, then the derivative is 0, which means that the tangent line will be horizontal. Now if the bottom dx dt is 0 and the top is not 0, then the tangent line is vertical. But if both of them are 0, then that's called a singular point. And there's no like set definition of what happens at a singular point. You just kind of have to do it for that particular problem. An example of a singular point is like a cusp. So here's another example of finding the derivative of a parametric equation. So again, for the first derivative, we just differentiate the two equations separately with respect to the parameter, and then we divide dy dt by dx over dt. And so we get the first derivative. Now for the second derivative, you do dy prime dt divided by dx dt. So again, if you draw it out, the dt's will again cancel out, and you'll just have dy prime over dx. And dy prime over dx is just the derivative of dy dx, so in other words, the second derivative. Now, if we want to find the arc length of a parametric curve from t equals a to t equals b, then we use this formula. And this formula is very similar to the regular arc length formula for non-parametric equations. And that's because we derive it in a similar way. So if we want to derive this equation, we just think about splitting up an arc that we want to find the length of into infinitely small parts. And if these infinitely small parts are small enough, we can approximate them as line segments. And we'll say each of these line segments has a length of ds. Now, we want them to be line segments because it's very easy to find the length of a line segment, because we just use the Pythagorean Theorem. So as you can see, ds is a hypotenuse, and the two sides are dx and dy, which are just very small changes in x and very small changes in y. So by the Pythagorean theorem, we get ds squared equals dx squared plus dy squared. And then we divide both sides by dt squared, take the square root of both sides, and then move the dt over. And then if we integrate both sides of this equation, the integral of ds, well, we're just adding up all these little lengths of the arc. So if we add up all of them, we'll just get the length of the whole arc, which is what we're looking for. And so we get the equation over here.